A pipeline valve can be perfectly compliant, correctly tagged, successfully pressure tested, and still be wrong for the service. That is the uncomfortable truth. You can buy the right size, the right pressure class, and the right valve type, yet still end up with the wrong sealing direction, the wrong seat philosophy, the wrong bore, the wrong cavity pressure behavior, the wrong actuator sizing, or the wrong material system. And many of those errors will not appear during procurement. They will appear after installation. They will appear during commissioning. They will appear when a pig reaches a partially open valve. They will appear when trapped liquid heats inside a body cavity. They will appear when an actuator cannot move a valve under full differential pressure. They will appear when a check valve slams after a pump trip. They will appear when maintenance teams discover that the drain, vent, or injection point cannot be reached. That is why API 6D should never be treated as a shopping list. It is a design framework. The standard gives you the baseline. You still have to provide the engineering intent. The first mistake engineers make is beginning with valve type. Use a ball valve, use a gate valve, put a check valve here. That sounds decisive, but it is often premature. The first question is not, what valve do I want? The first question is, what must this valve do? Does it need to isolate pressure, prevent reverse flow, permit pig passage, provide sectional isolation, support emergency shutdown, create double isolation, allow cavity venting, support maintenance, protect equipment during a transient, control inventory release, remain operable after years of inactivity? The valve is only the hardware selected to perform that function. Two valves with the same size and pressure class may behave completely differently. One may seal in both directions. Another may seal in only one. One may self-relieve cavity pressure. Another may trap it. One may pass an intelligent pig. Another may contain a step, seat intrusion, or reduced internal geometry that creates obstruction. One may provide tight shutoff with soft seats. Another may use metal seats and allow controlled leakage. So the real engineering principle is simple. Do not select the valve before you define the function. Pressure class creates another false sense of security. A valve marked Class 600 is not automatically suitable for every Class 600 application. Pressure and temperature are connected. Material capability matters. Seal capability matters. Transient pressure matters. Minimum temperature matters. Depressurization matters. Fluid composition matters. A metallic body may tolerate the design condition while the non-metallic seat, seal, or packing does not. You therefore need to look beyond nominal pressure class. You need maximum operating pressure, maximum design pressure, normal operating temperature, maximum design temperature, minimum operating temperature, minimum design metal temperature, startup conditions, shutdown conditions, emergency depressurization, hydraulic surge, gas expansion, potential Joule-Thomson cooling, trapped cavity pressure. The right question is not, can this valve hold the pressure? The right question is, can this complete assembly contain pressure and perform its intended function through every credible operating condition? That shift changes everything. The valve ends are another underestimated design boundary. For flanged valves, facing type, dimensions, drilling, finish, and compatibility must be correct. For butt-welded valves, the engineering becomes more critical. The valve end must match the pipeline. You need the correct nominal size, wall thickness, bore, material grade, specified minimum yield strength, and transition geometry. A poor weld end transition can create local stress concentration. It can complicate welding. It can obstruct pigging. It can create internal mismatch. It can create non-destructive examination difficulties. It can create a field problem that no amount of factory quality control can solve later. The valve to pipeline weld is not a minor fabrication detail. It is a system interface. Design control matters for the same reason. Inside one valve, pressure loads move through the body, seats, closure member, stem, bolting, and actuator interface. Change seat preload and leakage may improve, but operating torque may rise. Change elastomer and low temperature performance may improve, but decompression resistance may worsen. Increase wall thickness and weld end geometry may need to change. Change material and welding procedures may need revision. Change actuator torque and stem loading may increase. Change bore and pigging compatibility may change. This is why valve design must be documented, reviewed, verified, and controlled. A valve should not be accepted merely because it resembles something manufactured before. Similarity is not verification. Full opening, and reduced port also matter far more than many procurement documents suggest. This is not only about pressure drop. It affects pigging, it affects sphere passage, it affects inspection tools, it affects flow velocity, it affects erosion, it affects noise, it affects hydraulic behavior. A valve described as full bore should still be reviewed against the actual pigging requirement. What is the minimum internal diameter? Where is that minimum located? Is the bore concentric? Does the seat protrude? Are there steps? Are there cavities? Can debris collect? Can a partially open closure element interfere with the pig? Can the position indicator prove full opening? A trapped pig is not a minor inconvenience. It can become a major operational event. Gate valves can provide excellent full opening passage, but the generic label tells you very little. Is it wedge, slab, expanding, or double disc? Does it seal in one direction or both? How are the seats energized? Can cavity pressure build? Can the cavity relieve? Does that relief compromise isolation? Can the stem sealing system be maintained? Can solids collect in the body? Will the valve operate after years without movement? Does it need sealant injection? A gate valve that performs perfectly in a factory may behave very differently after years in buried service. Ball valves are equally easy to oversimplify. They are compact, quarter turn, and often highly effective, but ball valve does not define the engineering behavior. Is it floating or trunnion mounted? Are the seats soft, polymer, composite, or metallic? How do they respond to pressure? Is the valve bidirectional? Which side relieves cavity pressure? Can both seats isolate? Can trapped pressure develop? Can the valve perform under full differential pressure? Does it have injection systems? Is the stem protected against blowout? The seat arrangement is especially important. A closed valve with two effective seats can trap fluid in the cavity. If that fluid is liquid and temperature rises, pressure can rise rapidly. That pressure must go somewhere. Upstream, downstream, to whichever side is lower, through an external relief system. And what happens to your isolation philosophy when the cavity relieves? This is why double block and bleed cannot be treated as a complete requirement. 3 words do not define the hazard. You need to define what you are trying to achieve. Operational isolation, maintenance isolation, leak detection, product segregation, emergency isolation. Do you require 2 seating barriers? Do you require independent verification? Can one failed seat be tolerated? Can the cavity be vented? Can trap pressure occur? Can maintenance personnel safely rely on the arrangement? Only after those questions are answered should you select the hardware. A single valve with 2 seats is not automatically equivalent to 2 independent valves with a bleed between them. Plug valves bring their own logic. They can be robust and effective, but they may involve higher operating torque, lubrication, pressure balancing, and maintenance dependence. If the valve depends on sealant, can the correct sealant be used in the process fluid? Can it survive the operating temperature? Can maintenance personnel reach the injection point? Is the valve buried? Is the extension practical? A valve requiring maintenance access but installed without access is not a maintenance problem. It is a design failure. Check valves are probably the most misunderstood automatic valves. Engineers often select them by size and pressure class. That is not enough. Check valve behavior depends on flow velocity, disc inertia, hinge geometry, orientation, reverse flow development, and transient conditions. The most important question is not whether the valve closes. The question is how it closes. If it closes too late, reverse flow builds. When the disc finally closes, the reverse flow is arrested suddenly. That creates slam, surge, and mechanical impact. If the valve operates near an unstable position, it can chatter. Repeated impact can damage the hinge, disc, seat, or retaining parts. For critical systems, check valve selection should be connected to hydraulic transient analysis. A check valve is not passive decoration on a piping and instrumentation diagram. Material selection is another area where engineers stop too early. They specify body material and believe the material review is complete. It is not. You need to consider the body, bonnet, cover, bolting, stem, closure element, seat, spring, seal, packing, lubricant, overlay, and coating. A valve body may be suitable while the seat material is not. A seal may perform in dry gas and fail in aromatic condensate. An elastomer may swell in one fluid and shrink in another. A polymer may work at ambient temperature and become brittle at low temperature. Rapid gas decompression may damage seals after depressurization. The body can remain intact while the sealing system fails. Low-temperature service needs the same discipline. Do not stop at specifying a low-temperature body material. You need impact toughness for pressure-containing parts. You may need weld metal and heat-affected zone impact testing. You need compatible bolting. You need seals that remain functional. You need lubricants that remain usable. You need actuator performance at the actual temperature. And you need to consider abnormal cooling during depressurization. The lowest temperature may not occur during normal operation. It may occur during the exact emergency when the valve must work. Sour service also cannot be reduced to one note on the datasheet. Material grade matters. Heat treatment matters. Welding matters. Repair welding matters. Hard facing matters. Stem material matters. Bolting may matter. Hardness matters. A compliant base material can become non-compliant after uncontrolled fabrication or repair. That is why hardness control, welding procedure qualification, and manufacturing discipline are essential. Cavity pressure remains one of the most dangerous hidden failure modes. A closed valve traps liquid, temperature rises, the liquid expands, pressure increases, seats, seals, or body joints may become overloaded. The solution is not simply to add relief. You must know where the pressure relieves and whether that relief path compromises the isolation function. Every critical isolation valve should have a clearly understood cavity pressure philosophy. Small auxiliary connections also deserve more attention. Drain points, vent points, bypass connections, seat injection, stem injection. These are not accessories. They support testing, equalization, maintenance, depressurization, and emergency mitigation, but they are useful only if people can access them. A vent connection hidden under insulation is not useful. An injection fitting buried without extension is not maintainable. A bypass connection that cannot be operated safely does not support operations. Position indication is equally critical. A valve that appears open but is partially closed can obstruct a pig. A valve that appears closed but is not fully seated can defeat isolation. An actuator limit switch may prove actuator position without proving closure element position. For critical valves, mechanical indication, local indication, remote feedback, and diagnostic confirmation should be considered together. The more serious the consequence, the less you should depend on one indirect signal. The actuator and valve must be treated as one functional assembly. A correctly selected valve with an incorrectly sized actuator is an incorrectly selected valve. Actuator sizing must consider maximum differential pressure, seat friction, packing friction, bearing friction, temperature, aging, corrosion, lubricant condition, and required operating time. For pneumatic systems, use the minimum credible supply pressure. For gas over oil systems, consider the minimum available pipeline pressure. For electric actuators, consider duty cycle, speed, thermal limits, and power availability. An undersized actuator may fail to move the valve. An oversized actuator may damage the stem or internal parts. The objective is not maximum torque. The objective is reliable, controlled operation without mechanical overload. Hydrostatic testing is essential, but a past test does not prove long-term reliability. A shell test demonstrates pressure boundary integrity under defined conditions. A seat test demonstrates leakage performance under defined pressure, direction, and duration. It does not prove resistance to debris, thermal cycling, aging, corrosion, misalignment, poor installation, or years of inactivity. You also need to understand seat leakage criteria. Soft seats may be expected to show no visible leakage under defined conditions. Metal seats may permit controlled leakage. Demanding zero leakage from every metal-seated valve may sound conservative, but it may be technically unrealistic or unnecessary. Specify what the process needs. Do not specify what merely sounds strict. Test direction also matters. A unidirectional valve must be tested in the correct direction. A bidirectional valve must demonstrate both directions. A double isolation arrangement must be tested in a way that proves the intended function. A valid test certificate can still prove the wrong performance for your application. Quality assurance should therefore be risk-based. Material verification, welding qualification, non-destructive examination, dimensional checks, pressure testing, seat testing, functional testing, actuator stroke, Coding inspection. Documentation. Witness the things that cannot be verified later. Do not create inspection activity for appearance. Create inspection control for risk. Even the final draining and preservation process matters. Residual hydrotest water can corrode internal parts. It can freeze. It can contaminate the process. It can damage sealing surfaces. A valve can leave the factory after passing all tests and still begin degrading because it was not properly drained, dried, lubricated, and preserved. Storage can undo good manufacturing just as easily. Flange faces need protection. Weld ends need protection. Internal surfaces need preservation. Actuators need weather protection. Valves must be lifted from approved points. They should not be dragged, forced, or stored carelessly. A valve can be damaged before it ever sees process pressure. Installation can create the final failure. Do not use flange bolts to pull misaligned piping into position. Do not force a heavy valve into a stressed line. Do not ignore actuator support. Do not expose soft seats to uncontrolled welding heat. Do not allow debris into the body. Do not treat the valve as a structural correction device for poor construction. Operations then needs a clear philosophy. Which direction does it seal? Where does cavity pressure relieve? Can the cavity be vented? Can seat leakage be verified? Can the valve close against full differential pressure? Should pressure be equalized before opening? What does abnormal torque mean? Can emergency sealant be used? What happens if power is lost? Can the valve be operated manually? A sophisticated valve that operators do not understand is not a reliable valve. Maintenance must also be engineered from the start. Can technicians reach the vents? Can they access the injection fittings? Can the actuator be removed? Can the gearbox be serviced? Can stem sealing areas be inspected? Can cavity pressure be confirmed before work begins? Can the valve be maintained without creating an unacceptable operational risk? Accessibility is part of engineering. The most common valve failures often begin with simple assumptions, assuming every ball valve is bidirectional, assuming full bore means piggable, assuming pressure class proves complete suitability, assuming double block and bleed means the same thing to everyone, assuming metal seats provide zero leakage, assuming factory testing proves lifetime reliability, assuming the actuator will operate the valve under worst-case differential pressure, assuming maintenance access can be solved later, assuming the standard will fill in missing design intent. It will not. The corrective action is not to produce a longer specification filled with copied clauses. The corrective action is to define the function clearly, define the hazard, define the pressure source, define the flow direction, define the required isolation, define the cavity behavior, define the bore, define the pigging need, define leakage expectations, define materials, define temperature, define sour service conditions, define actuator duty, define testing, define maintenance. Then ask the manufacturer to demonstrate how the proposed design meets that requirement. That is engineering. API 6D provides the structure, then the vendor provides the equipment, but you provide the intent. And when the intent is weak, the equipment can be compliant while the system remains wrong. So the final question is not, does this valve meet the standard? The final question is, will this valve continue to perform the required function under the worst credible condition 10 or 20 years after installation? That is the question worth asking. That is the question that separates valve procurement from valve engineering. Share your experience in the comments. Have you seen trapped cavity pressure, seat leakage, actuator failure, pigging obstruction, wrong flow direction, check valve slam, inaccessible maintenance points, or poor weld end compatibility? What valve specification mistake has caused the biggest field problem in your projects? Add your views, lessons, and technical opinions below, because practical engineering knowledge becomes valuable when experienced people challenge assumptions openly. Like this episode, share it with engineers who work in design, projects, operations, commissioning, and maintenance. And subscribe to the channel for more engineering standards simplified into practical design decisions. Follow my LinkedIn newsletter for deeper engineering design, project management, reliability, and technical leadership discussions.